to define what is the capacitance of a, could be of a capacitor, but could be of any conductor. So we have here, let's say a conductor plate with positive charge Q, and here another conductor plate with the same amount of charge but with the opposite charge. The electric field that is generated will only count in this part between the plates, as we saw on previous video with Gauss law, because here the electric field in this part generated by this conductor plate is in this direction. These are the electric field lines, and for this negative conductor plate is in this direction. The electric field lines goes towards the negative charge and away from the positive charges. So the electric field here is epsilon is sigma, that is the surface charge density divided by epsilon naught. The electric field will also be 0 here, well, approximately 0 here and approximately 0 here. The electric field only due to one charge, to one plate. If we take as if you were an infinitely plate with uniformly charged, the electric field is of only this plate is 2 coulombs constant times P times the surface charge density. Then, because we have the contribution of this plate and of this plate, actually we have that this total electric field total is twice this amount, so it will be 4 times coulombs constant times P times sigma. Then we have that the energy is measured in joules, and this will be the work done. The work is equal to force times distance, and the work done per charge is the same as the electric field times the distance, and this is called the voltage. So the electric field times the distance of separation, this could be L, could be, then the voltage would be 4K P sigma times L. Then sorry, this is the electric field times times the distance. The electric field would be also if sigma is equal to the charge divided by area. Then here we have 4 times K times P times the charge divided by area times the distance of separation. If we want the charge per voltage, so we will divide everything by 4, here everything by 4 K P L, and here divided by 4 P K L, and multiply everything by area. Then we have that the and then divide everything by voltage. We have that the charge divided by voltage is equal to then here I cancel all this with this L with this L, this area with this area, and so in this side I just have charge divided by voltage is equal to the area divided by 4 P K L. So that means that the charge or the relationship between the charge and the voltage is always constant, and that constant is just this, that is the area of one of the plates divided by 4 P coulombs constant times the distance of separation. If we want to put it in other way, we have Coulomb constant is 1 over 4p epsilon naught. So here we have that charge divided by voltage is area divided by 4pl times 1 over k, but k is 1 over 4p epsilon naught. So this will pass here, and then we will just have that the charge per voltage is equal to the area times epsilon naught divided by L, or D, whatever you want to call it. That is the distance of separation. And this ratio is always constant for a fixed condenser. This system is called a condenser or a capacitor. And this is a measure of how much charge or how much energy could be stored in between these plates. That the energy that could be stored, we will see it in the next video. So this constant, the charge divided by voltage, is a constant for a fixed capacitor that only depends on the intrinsic factors of the capacitor, that is the area and the distance of separation. So this constant is called capacitance. Capacitance or capacity. The units are what we called farads. That would be coulomb per volt. So 1 farad is 1 coulomb per volt. So we usually write that the capacitance of a condenser or a capacitor is the charge divided by the voltage. Other way to do it is, we know that the electric field is, this is the electric field, voltage is electric field times the distance or the area, the separation. So the voltage is sigma divided by epsilon naught times L. This is the voltage, and the charge, well, we'll just put it as, charge is sigma times area. So we have that charge divided by voltage is sigma times the area divided by sigma epsilon sub naught L, and so this goes to area epsilon naught divided by L, and so this again is the capacitance or capacitor of this condenser or capacitor. For a sphere, we usually think as the capacitance, let's say, of only a sphere, when we don't have like a spherical condenser. We don't have this, in which we could say this is one plate and this is the other. If we just have a sphere, we could say that the capacitance of this sphere is C. We will see what is C in this case, but this is because when we say just the capacitance of a sphere, we imagine that this is one plate and the other plate is a plate that is again a sphere but has a radius of infinity. So the capacitance of this sphere would be charge per voltage. Again, the voltage is the electric field times the distance. The distance is could be the radius. This is the voltage. So the capacitance would be charge per voltage. We also know that the electric field is force divided by Q2, and the force is Coulomb's constant times Q1 times Q2 divided by R squared, and then divided by this Q2. So we have that the electric field, it's just K times Q1 divided by R squared. So we have that the capacitance of a sphere is the charge Q divided by this. The electric field is Coulomb's constant times Q1 times Q1 times the radius divided by r squared. I would kill this and this, so I just have that the capacitance is r divided by k, or k, because k is equal to 1 over 4p epsilon sub naught, then c would be equal to 4p epsilon naught times the radius of the sphere. So this is the capacitance of a sphere. So this is the capacitance that is measured in farads, and in the next video we will see what is the energy that could be stored in this condenser.